Dear student, in this session we will discuss the subtopic 4.2 Part B Types of Scheduling Algorithm from Unit number 4 CPU Scheduling and Algorithms. Now the course outcome is you will able to apply the scheduling algorithm in order to calculate the turnaround time and the average waiting time, and the learning outcome is you will able to write a program to calculate the total waiting and turnaround time for n number of processes. So in the previous part, we already discussed the first come first serve, shortage of first and shortest remaining time, these three algorithms. Now in this session, we will discuss the priority scheduling and the round robin scheduling. Now, the priority scheduling algorithm. The priority scheduling algorithm, it is associated with each process. So, the CPU is allocated to the process with the highest priority. That means the integer number which is smallest will have the highest priority. Then, say for example, if the equal priority processes are scheduled, then the execution takes place in the FCFS manner, that is the first come and first serve. The SJF is priority scheduling where the priority is inverse of predicted next CPU burst. What this means is that, say for example, if the burst time is larger, then the lower the priority and vice versa. That means if the burst time is smaller, then the priority will be higher. Then the priorities can be defined either internally or externally. So some of the internal priorities may be defined as the time limit, then the memory requirement, then the number of open files, and the ratio of average IO burst to the average CPU burst. So this have to be used in the computing priorities. Another one is the external priorities. In the external priorities, the priorities will be something like the importance of the processes, then the time and amount of fund being paid for the use of the computer, then the department sponsoring the work, or any other political or the other factors. So these comes under the external priorities. The priority scheduling, again, it can be preemptive or non-preemptive. So the one of the problem with the priority scheduling is that it has the indefinite blocking or starvation. Now what this means is that a process is ready to run, but waiting for the CPU may block the process. That means sometimes the low priority process may never get executed. So in order to remove this particular drawback, the solution is aging. Now what we used to do in the aging? So aging, it is nothing but a technique in which we gradually increase the priority of the process that waits in the system for a longer period of time, so that sometimes or in some way the process will able to execute even if it is uh, available in a queue for a longer period of time. Now let us discuss the example of priority scheduling. Now here within our ready queue we have total 5 processes with priorities as 3 to process P1, 1 priority. So 1 is the highest priority, the smaller the number, the higher the priority. Then the second highest priority is to process P5, then to process P1, then to process P3, and later on P5. Now the process with the highest priority is P2 with the burst time as 1. So first of all, the process get executed is P2 for the burst time, that is 1 millisecond. The second highest priority is of P5 with the burst time as 5. So the P5 executed from 1 to 6 6, that is total 5 milliseconds. And then the next priority is of process P1 with the burst time as 10. So now from 6 to 16, that is 10 milliseconds, the P1 process get executed. Then the next priority is of process P3, that is the 4 priority with the burst time as 2. So for 2 millisecond process P3 will get executed, and the last process, that is process P4, having the priority as 5, get executed for 1 millisecond, so that is from 18 to 19. So this is how all the processes get executed one after the another according to the priority given over here. Now, calculating the average waiting time for it is, say for example, the waiting time for P1 is 6, as P2 is executing over here for 1 millisecond, P5 is executing for next 5 milliseconds, so total 6 milliseconds P1 is waiting. So the waiting time for P1 is 6. The waiting time for P2 is 0, as it has the highest priority. It start executing as soon as it enters into the ready queue. Then process P3. So this is the waiting time for process P3, that is 16. Then this is the waiting time for process P4, that is from 0 to 18. So 18, and the waiting time for P1 is the 1 millisecond. So this is what 1 millisecond. So adding all the waiting times of all 5 processes and dividing it by 5 gives us the average waiting time. At the same time, let us discuss over here how to calculate the average turnaround time. The average turnaround time, it is nothing but the time which is the time spent in the waiting state, as well as the time in the execution period. So here we can see that process P1 is waiting from 0 to 6 millisecond and executing from 6 to 16 milliseconds. So total time for P1, turnaround time for P1 is 16. Then for P2, the executing time is 1 and waiting time is 0. So the turnaround time for P2 is 1. In the same way, the turnaround time for P3 is 18, as the waiting time is 16 plus executing time is 2. So that's why it is 18. Then for P4, the turnaround time is, the total waiting time is 18 and the executing time is 1. So total turnaround time for P4 is 19, and for P5, the waiting time is 1 and the executing time is 5. So total 6 is the turnaround time for P5. So adding all these times, turnaround times of every individual process and dividing it by 5 will give is the average turnaround time. Then let us discuss the another scheduling algorithm, that is the round robin scheduling algorithm. Now this particular algorithm, that is the round robin algorithm, it is specially designed for time sharing systems. So it is similar to scheduling, that is FCFS scheduling, but the preemption is added in order to switch between the processes. That means in the round robin scheduling, every process get executed for fixed amount of time, and we used to call it as a time quantum, usually as Q. Now each process get a small unit time, so that is what we call it as a time quantum, that may be usually 10 to 100 milliseconds depending upon the operating system setting. After this time has been elapsed, the process is preempted. That means automatically the process get stopped even if the process is not completed. It is preempted, and then it is again added to the ready queue, so that it will continue its execution later on from where it has been stopped. If there are n processes in the ready queue and the time quantum is q, then each process gets 1 by n of the CPU time in chunks of at most q time units at once. So no processes in the round robin scheduling waits more than the n minus 1 into q time units. Timer is there, or we used to call it as a timer interrupts will after every quantum to schedule the next process. Now the performance related issue is that, say for example, our time quantum, that is q, is very large, then this round robin it will work as first come first serve, that is the FIFO queue. If this particular time quantum is very small, then in that case what will happen, the overhead the context switching will be large one, otherwise the overhead is too high. So these are some of the plus points as well as things related to the round robin scheduling. Now let us discuss the example related to round robin scheduling. Let us say that the time quantum for this particular we will set as 4 milliseconds. Now within our ready queue we have three processes, that is process P1 with burst time as 24, process P2 with burst time as 3 and process P3 with burst time as 3. Now our time quantum is 4. So the net chart we can see over here is that for the first, since it is the round robin and it will start executing first come first serve for the fixed time quantum. So the first process is P1. So P1 get executed for first 4 milliseconds since the time quantum is 4. And once the 4 millisecond get completed, it gets preempted over here and the next process in the queue get executed. Now our next process is P2 with burst time as 3 get executed for 3 millisecond over here. Even if the our time quantum is 4, since our burst time for P2 is 3, so this will keep the CPU for 3 milliseconds only, and then it will give to the next process in the queue, that is P3. Again the P3 has the burst time as 3, so it get executed for next 3 milliseconds and will give the CPU to again to the process P1, because now we can see that P2 and P3 has completed its execution. Now the remaining process is P1 with remaining burst time as 20. So after that, for each 4 milliseconds, that is total 5 times the process get executed, that is P1, because P1 is the only process in the ready queue. So typically the higher average turnaround has been there for the SJF, but the very important advantage is the response time is better. So here we can see that the average waiting time for P1 is 6. Since here you can see that P1 is executing over here, and from 4 to 10 it is not executing. So this is the average waiting time for P1, and in the rest of the time slot we are able to see that the P1 is in running state. So 6 is the waiting time for P1. Then for P2 the waiting time is 4, and for P3 the waiting time is 7. Okay, so this is 7. So divided by 3. So this is how the average waiting time for this particular is 5.66 millisecond. Then the average turnaround time is for P1, it is the time in waiting state as well as it in executing state. So total time is 30. So for P1 the turnaround time is 30. Then for P2 the waiting time is 4 and executing time is 3 plus that is 7. So total turnaround time for P2 is 7. Then for P3, the waiting time is 7 plus executing time is 3. So total 3 plus 7 is 10, and that divided by 3. So average turnaround time for this is 16.66 minutes. So Q should be large as compared to context switch. So usually the Q, that is the quantum, it should lie between 10 milliseconds to 100 milliseconds, as the context switch time is generally less than 10 microseconds. So here we can see that, say for example, we have the process time is of 10 milliseconds. If the quantum is of 12 milliseconds, then in that case the context switch is 0. If the quantum is 6 millisecond, then the context switch is once. It will execute continuously for 6 millisecond, then the context switch is there, and then rest of the 4 millisecond it will execute. So one context switch is there. Then if the quantum is 1, then in that case the context switches will be 9. So here we can count that after every 1 millisecond quantum there is a context switch. So in this way total 9 context switches will be there. So the time quantum, it should be not too much small as well as too much. So this is all about the priority scheduling and the round robin scheduling. In the next session, we will discuss the multi-level queue scheduling. Thank you.